Right now, scattered across the galaxy, black holes are waiting, silent predators lurking in the darkness, their gravitational field so intense that nothing can escape once it crosses the event horizon. Not matter, not energy, not even light itself. But what actually happens if you fall into one of these cosmic monsters? The answer is far more terrifying and strange than you can imagine, because you don't just die. You experience impossible physics that tears apart everything you thought you knew about space, time, and reality. Your journey from the moment you approach a black hole to the instant you reach its center will stretch seconds into eternities, freeze you in time forever from an outside perspective, and ultimately destroy you in ways that violate the very laws of quantum mechanics. Hit that like button and subscribe as we trace the complete timeline of the most horrifying journey in the universe. Prepare yourselves. We begin. Let's start with the setup. You're an astronaut, drifting through space, perhaps investigating reports of missing ships, or following a mysterious gravitational anomaly. Your instruments detect something ahead, a region where stars disappear from view, where space itself seems to curve inward toward an invisible point. You found a stellar mass black hole, perhaps 10 times the mass of our Sun, compressed into a sphere roughly 60 kilometers across. From your current distance of several thousand kilometers, it appears as a perfect circle of absolute darkness surrounded by a bright ring where light from background stars gets bent and distorted by extreme gravity. This is your first view of the event horizon, the boundary of no return. It's not a physical surface, but an imaginary boundary in space where the escape velocity equals the speed of light. Outside this boundary, you can still escape if your engines are powerful enough. Inside, escape becomes impossible regardless of how powerful your engines are. The speed of light is the ultimate speed limit, and if you'd need to exceed it to escape, then you're trapped forever. Around the event horizon, you notice something strange. A shimmering accretion disk of superheated matter spirals inward, gas and dust from nearby space falling toward the black hole and heating to millions of degrees through friction and compression. This disk glows brilliantly in X-rays and visible light, ironically making the black hole one of the brightest objects in the galaxy despite its darkness. Jets of matter and energy shoot outward from the poles, perpendicular to the disk, as the black hole's magnetic field channels some infalling material back into space at nearly light speed. But you're not approaching the accretion disk. Your trajectory will take you directly toward the event horizon on a path clear of the superheated plasma. As you drift closer, still thousands of kilometers away, you begin to notice gravitational effects. Your instruments detect tidal forces, differences in gravitational pull between your head and feet. These forces are still negligible, barely perceptible, but they're growing stronger with every passing moment. At 1,000 kilometers from the event horizon, the tidal forces become noticeable. If you're falling feet first, your feet experience slightly stronger gravity than your head. The difference is small, perhaps equivalent to an extra kilogram of weight on your feet, but it's measurable and increasing. This tidal stretching is called spaghettification, and it will eventually tear you apart. For a stellar mass black hole, that won't happen until you're much closer. But for a smaller black hole, you'd already be experiencing lethal forces. Your velocity is increasing rapidly now. Gravity accelerates you toward the event horizon at ever greater speeds. At 1,000 kilometers out, you're falling at perhaps 100 kilometers per second. By the time you reach 500 kilometers, you're moving at several hundred kilometers per second. The black hole's immense gravity well is pulling you in, converting gravitational potential energy into kinetic energy. You're picking up speed without firing any engines, falling freely through increasingly curved space-time. At this distance, you notice another strange effect. Light behaves oddly near the black hole. Photons passing close to the event horizon get bent by gravity, their paths curving as they travel through warped space-time. This gravitational lensing creates distorted images of stars and galaxies behind the black hole. You see stars that should be blocked by the black hole appearing around its edges, their light bent around the event horizon by extreme space-time curvature. Some photons orbit the black hole in a circular path called the photon sphere. Located at 1.5 times the event horizon radius for a non-rotating black hole. At 300 kilometers from the event horizon for our 10 solar mass black hole. Photons can orbit indefinitely in a precarious balance between gravity pulling them inward and their tangential velocity carrying them forward. This creates a bright ring around the black hole where orbiting photons accumulate before eventually falling in or escaping outward. You're falling past the photon sphere now, entering a region where light itself cannot escape in all directions. If you point a laser outward away from the black hole, the beam will curve back inward. Only light aimed within a narrow cone directly away from the black hole can escape. This cone narrows as you approach the event horizon, until at the horizon itself, only light aimed exactly perpendicular to the surface can escape, and even that light remains frozen at the horizon forever from an outside perspective. At 100 kilometers from the event horizon, relativistic effects become dramatic. Time dilation, predicted by Einstein's general relativity, means that your clocks run slower in the black hole's intense gravitational field. Compared to clocks far from the black hole, your watch ticks more slowly. This isn't an illusion or measurement error. Time genuinely passes more slowly for you than for observers far away. The closer you get to the event horizon, the more severe this time dilation becomes. An observer watching from a safe distance with a powerful telescope would see something extraordinary. As you approach the event horizon, they see you moving more and more slowly. Your movements appear sluggish, as if you're swimming through syrup. The light from your suit gets progressively more redshifted, stretched to longer wavelengths by the gravitational field. You appear to dim and redden, fading gradually from view. From the distant observer's perspective, you never actually reach the event horizon. As you approach it, your image asymptotically approaches the boundary, slowing down more and more, taking infinite time to actually cross. They see you frozen at the event horizon forever, your image growing dimmer and redder, eventually fading to imperceptibility. Your information, the pattern of light and matter that constitutes your observable existence, remains smeared across the event horizon from the outside perspective. But your experience is completely different. You don't feel yourself slowing down. Your clocks appear to tick normally from your perspective. You see the event horizon approaching at increasing speed as you fall toward it. The universe behind you appears to speed up. Billions of years of cosmic history flash by in moments as time dilation accelerates the outside universe from your viewpoint. You might see stars evolve and die, galaxies merge and separate, the universe itself aging at tremendous rate. This is the first major divergence between perspectives. An outside observer sees you frozen forever at the event horizon. You experience falling through the horizon in finite time, perhaps just minutes or hours depending on your initial distance. Both perspectives are valid within their own reference frames. There's no absolute truth about when you cross the horizon. The answer depends on whose clock you're using to measure time. At 50 kilometers from the event horizon, the tidal forces are becoming significant. The gravitational difference between your head and feet now amounts to hundreds of kilograms of force, stretching your body noticeably. Your bones creak under the strain. Blood pools in your feet as gravity pulls more strongly there than at your head. If you weren't already dead from other causes, you'd be experiencing extreme discomfort verging on agony as your body stretches like taffy. The escape velocity at this distance exceeds 99% of light speed. There's no returning to normal space. Even if you had the most powerful rocket engines imaginable, you couldn't generate enough thrust to escape. The space-time curvature is so extreme that all future paths lead inward toward the singularity. This is a one-way journey now, though you won't cross the point of no return until you reach the event horizon itself. At 10 kilometers from the event horizon, reality becomes increasingly alien. Space-time is so warped that the normal rules of geometry break down. Straight lines curve dramatically. Parallel lines converge. Light takes bizarre paths through the twisted geometry. Looking back toward the universe you left behind, you see the cosmos compressed into a shrinking circle directly behind you. All the stars and galaxies squeezed into an increasingly narrow cone as extreme lensing bends light around the black hole. The tidal forces are now thousands of times Earth's gravity, stretching your body several meters longer than normal. Your molecular bonds are straining. The atoms in your body are being pulled apart as the gravitational difference between your head and feet overcomes electromagnetic forces holding your molecules together. You're no longer recognizably human-shaped, stretched into a long, thin strand of matter falling toward the event horizon. 1 kilometer from the event horizon, you're moving at 99.9% of light speed, relative to observers far from the black hole. Though from your perspective, you're in free fall and feel weightless. The universe behind you has aged billions of years in what feels like minutes to you. If you could survive and observe, you might see stars exhausting their fuel, supernova explosions, entire galactic evolution compressed into brief moments, and then you cross the event horizon. From your perspective, nothing special happens at this moment. There's no physical boundary, no surface to pass through, no sensation marking the transition. You simply continue falling, noticing only that the tidal forces keep increasing and the view behind you continues distorting. You've crossed the most famous boundary in physics, and you didn't feel a thing. But something profound has changed. You've entered a region of space-time from which no escape is possible. Every future path leads inward toward the singularity. Time and space have exchanged roles in a precise mathematical sense. Outside the event horizon, you can move freely in space but must move forward in time. Inside the event horizon, you can move freely in your time direction, but you must move inward in space toward the singularity. Moving toward the singularity isn't a choice. It's as inevitable as moving forward in time was outside. This role reversal is hard to grasp intuitively. The singularity isn't a place in space that you're falling toward. It's a moment in your future, an instant you will inevitably reach, just as you inevitably reach future moments when outside the black hole. You cannot avoid the singularity any more than you can avoid tomorrow. It's in your future, and time flows inexorably forward, carrying you toward it. Inside the event horizon, the tidal forces escalate catastrophically. Within seconds, your body has been stretched to hundreds of meters long and compressed to millimeters wide. You're a thin strand of atoms falling toward the center. The electromagnetic forces binding your molecules have been overwhelmed completely. Your atomic structure disintegrates as gravitational tidal forces exceed nuclear binding energies. At this point, You're no longer conscious or alive in any meaningful sense. Your brain has been disrupted beyond any possibility of function. The neurons firing thought are scattered across vast distances relative to their normal spacing. But let's continue following what's left of you. The component particles that once formed your body, now a stream of separated atoms falling toward the singularity. The journey to the singularity from the event horizon takes less than a second for a stellar mass black hole. For a supermassive black hole billions of times more massive, it could take hours. But either way, the endpoint is the same. The tidal forces increase without limit as you approach the center. The atoms that were your body are torn into subatomic particles. Protons and neutrons are ripped into their constituent quarks. Even quarks might be torn apart into more fundamental entities if such things exist. According to classical general relativity, the singularity is a point of infinite density and infinite space-time curvature. All the matter that fell into the black hole is compressed to infinite density at this mathematical point. The equations of general relativity break down completely. They predict infinity for physical quantities, which signals that the theory cannot describe what happens at the singularity. This breakdown isn't just a technical problem. It represents a genuine boundary of knowledge. General relativity has been spectacularly successful at describing gravity everywhere else, from planetary orbits to gravitational waves to black hole event horizons. But at the singularity, the theory fails. It tells us that it cannot be trusted. Something else must take over. Some theory we don't yet have that can describe physics at infinite density and curvature. Most physicists believe quantum gravity will resolve the singularity. When densities become extreme enough, quantum effects of space-time itself should become important. Space and time might be fundamentally discrete at the Planck scale, made of quantum units that cannot be subdivided further. If so, compression cannot continue to infinite density. It must stop at some maximum density related to the Planck density, about 10 to the power of 96 kilograms per cubic meter. This would replace the singularity with a region of extreme but finite density, perhaps with exotic physics that we cannot currently describe. Some theories propose that black hole interiors connect to other regions of spacetime through wormholes, or that they bud off into separate baby universes, or that quantum effects cause them to bounce, creating white holes that expel matter into other regions. All of this is speculation because we lack a complete theory of quantum gravity. But let's return to the timeline. What actually happens to the particles that were you when they reach the central region, assuming we follow classical general relativity to its conclusion? They encounter infinite tidal forces. The distance between particles becomes meaningless because space-time curvature becomes infinite. Time itself ends at the singularity in the sense that world lines, the paths particles follow through space-time, terminate there. There's no future beyond the singularity, no continuation of existence, no passage into some other state. It's a genuine endpoint where the mathematics stops. This raises the information paradox that has troubled physicists since Stephen Hawking's work in the 1970s. Quantum mechanics demands that information cannot be destroyed. The quantum state describing a system must evolve according to unitary transformations that preserve information. But if matter falls into a black hole and reaches a singularity where it's destroyed, the information describing that matter's quantum state appears to be lost. This violates fundamental principles of quantum mechanics. Some proposed resolutions suggest information is preserved on the event horizon, encoded in subtle correlations in the Hawking radiation emitted by the black hole. Others propose that the singularity doesn't actually destroy information, but transforms it in ways we don't understand. Or perhaps information is fundamentally lost, requiring modifications to quantum mechanics. The paradox remains unresolved and represents one of the deepest problems in theoretical physics. But we've been following your perspective inside the black hole. Let's return to what observers outside see during this entire process. From the moment you started falling until billions of years in their future, they see you approach the event horizon asymptotically, never quite crossing, your image frozen at the boundary, growing dimmer and redder as photons climbing out of the gravitational well lose energy to redshift. Hawking radiation complicates this picture. Quantum effects near the event horizon cause black holes to slowly evaporate, emitting thermal radiation that carries away mass. Over timescales of 10 to the power of 67 years for a stellar mass black hole, the entire black hole evaporates completely. From the outside perspective, you appear frozen at the horizon during all this time. When the black hole finally evaporates, what happens to your frozen image? This is another aspect of the information paradox. The thermal Hawking radiation appears to contain no information about what fell into the black hole. It's like burning a book and trying to reconstruct the text from the heat and light of the flames. If your information is truly encoded on the event horizon, as some theories suggest, then as the black hole evaporates, that information must somehow be transferred to the outgoing Hawking radiation. How this happens remains mysterious. Recent developments in holography and quantum gravity suggest that the event horizon might not be a smooth, featureless surface, but instead have quantum structure that encodes information. The firewall proposal suggests that observers falling through the event horizon might encounter high-energy particles created by quantum effects, incinerating them at the boundary rather than allowing smooth passage to the interior. This contradicts the equivalence principle, which states that free fall should feel the same everywhere, including at the event horizon. These theoretical difficulties reveal that we don't fully understand black holes. The smooth classical picture of an event horizon and interior breaks down when we include quantum effects. The true nature of the horizon and what happens to infalling matter remains an open question that likely requires a complete theory of quantum gravity to resolve. Now let's consider different types of black holes and how they change the timeline. We've been describing a Schwarzschild black hole, a non-rotating, uncharged black hole that's perfectly spherical. Real black holes rotate, often rapidly, because they form from collapsing stars that were rotating. Rotation dramatically changes the black hole structure and the experience of falling in. A rotating black hole called a Kerr black hole has several additional features. The event horizon is surrounded by a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. In this region, nothing can remain stationary. Even light must rotate in the direction of the black hole's spin. You'd be dragged around the black hole as you fell inward, following a spiraling path rather than falling straight in. The ergosphere's dragging effect becomes extreme close to the event horizon. You'd be whipped around the black hole at tremendous speeds, experiencing enormous centrifugal forces in addition to tidal forces. For a maximally rotating black hole, the rotation speed at the event horizon approaches the speed of light. The stresses from this rotation would tear you apart even before tidal forces became dominant. Inside a rotating black hole, the structure is even stranger. The singularity isn't a point, but a ring, a circular region where space-time curvature becomes infinite. Approaching this ring singularity from certain angles might theoretically allow you to pass through without encountering infinite tidal forces. though you'd still be destroyed by finite but enormous forces. Some solutions to Einstein's equations suggest that passing through the ring might lead to other regions of spacetime, perhaps even other universes, though these solutions likely aren't physically realistic. Charged black holes, called Reissner-Nordstrom black holes, have two event horizons. An outer horizon functions like the standard event horizon, but inside exists a second inner horizon called the Cauchy horizon. Between these horizons, conditions are relatively calm. Tidal forces aren't overwhelming. In principle, you could survive the journey from outer to inner horizon. But at the Cauchy horizon, something terrible happens. Infalling matter and radiation from the entire history of the universe gets blue shifted to infinite energy as it crosses this inner boundary. You'd encounter infinitely energetic radiation that would destroy you instantly. The mass inflation instability makes the Cauchy horizon effectively impassable. You cannot reach the exotic inner regions that the mathematics describes. Moreover, astrophysical black holes are probably never precisely charged because they quickly neutralize by attracting opposite charges from surrounding space. Charged black holes are likely mathematical curiosities rather than physical realities, though they're useful for understanding the general structure of black hole solutions. Supermassive black holes, the giants lurking at galaxy centers containing millions or billions of solar masses, provide a gentler experience for an infalling observer. Because tidal forces depend on the gradient of gravity, they're weaker near the event horizon of larger black holes. For a billion solar mass black hole, tidal forces at the event horizon are only about 1/1,000,000th of Earth's gravity. You could cross the event horizon completely intact, unaware anything special had happened. You'd survive for minutes or even hours inside a supermassive black hole before tidal forces became lethal. This extended survival time is both blessing and curse. You'd have time to observe your surroundings, to contemplate your fate, to experience the bizarre physics of the black hole interior. But you'd also have time to feel terror as you realize escape is impossible and destruction inevitable. The view from inside a supermassive black hole would be extraordinary. Looking back toward the event horizon, you'd see the universe you left behind compressed into a bright spot, all external reality visible through the hole you fell through. Due to light travel time and gravitational lensing, you might see multiple images of the same objects at different times, watching events unfold in strange sequences as light takes different paths through the warped space-time. Looking toward the singularity, you'd see absolute darkness, a void where no light comes from. Any photons emitted from deeper in the black hole travel inward toward the singularity, unable to reach your position. The singularity is in everyone's future inside the event horizon, so no information from it can propagate back to earlier moments. You're seeing a true boundary of space-time, a moment in the future that absorbs all light and matter without returning anything. As you fall toward this singularity over minutes or hours, tidal forces gradually increase. Eventually, they exceed the structural strength of your body, pulling you apart. Then they exceed molecular binding energies, atomic binding energies, nuclear binding energies. You're disassembled scale by scale as you approach the central region. Even for a supermassive black hole, the endpoint is the same. Destruction at scales we cannot currently describe physically. Throughout this timeline, one question looms. What is it like to die in a black hole? The answer depends on when you consider consciousness to end. If consciousness requires functioning neurons, you lose consciousness when tidal forces disrupt your brain structure, probably within seconds of crossing the event horizon for a stellar mass black hole, or within minutes for a supermassive black hole. But this raises philosophical puzzles. If your consciousness depends on information patterns rather than specific atoms, does consciousness persist in some form as those patterns get encoded on the event horizon from an outside perspective? If information isn't destroyed, if it's preserved in Hawking, radiation or horizon structure, does that mean some aspect of you survives the black hole's eventual evaporation? These questions venture into philosophy of mind and personal identity. Physics cannot answer what constitutes your subjective experience or when it genuinely ends. We can describe what happens to matter and information, but the relationship between physical processes and consciousness remains mysterious. Falling into a black hole doesn't resolve these mysteries. It simply places them in the most extreme context imaginable. There's also the question of what you'd feel during the fall. Ignoring the fatal tidal forces for a moment, you'd be in free fall the entire time, experiencing weightlessness. Einstein's equivalence principle states that free fall is locally indistinguishable from floating in empty space far from any gravity. You wouldn't feel the black hole pulling on you because you're falling freely through its gravitational field. This means the journey might be peaceful in some sense, at least until tidal forces become overwhelming. You'd float weightlessly, watching the universe you left behind age rapidly, seeing space-time distort in impossible ways around you, but not feeling the tremendous gravitational forces because you're falling with them rather than resisting them. Death would come from stretching, from your body being pulled apart by differential gravity, not from feeling crushed by gravitational weight. The psychological experience would likely be terrifying regardless of the physical sensations. Knowing you're trapped, that escape is impossible, that destruction is inevitable and approaching, would create existential horror that physical pain might barely register against. You'd have time to understand your fate, to accept your mortality, to experience the strange privilege of witnessing physics that no one has survived to report on. Some physicists have speculated about whether advanced civilizations might use black holes for time travel or accessing other universes. The mathematics of rotating black holes includes solutions showing paths through the ring singularity that lead to other regions of space-time. If these solutions were physically realistic, you might theoretically enter a black hole and emerge in another time or place. But the consensus is that these exotic pathways aren't stable or traversable. Quantum effects probably prevent smooth passage through the extreme conditions near singularities. Even if the path existed mathematically, traveling it would require surviving conditions that would destroy any physical object. The time travel and wormhole solutions are likely artifacts of extending general relativity beyond where it's valid, describing situations that cannot actually occur in nature. Near the end of your journey, in the final moments before reaching the singularity region, quantum effects might become important. If space and time are fundamentally discrete at the Planck scale, then the classical picture of smooth, continuous spacetime breaks down. You might encounter a quantum regime where our current theories cannot describe what happens. The nature of time, space, matter, and causation might be so different from ordinary experience that no description in familiar terms is possible. This is where physics reaches its current boundary. We can follow your path up to this point, using general relativity, describing how space-time curves and how you move through that curvature. But at the singularity, or whatever replaces it, we need new physics, string theory, loop quantum gravity, or some other quantum gravity framework must take over to describe the endpoint of your journey. The full timeline of falling into a black hole spans from the initial approach through the event horizon crossing that separates your experience from external observers forever, to the final encounter with the singularity or its quantum replacement. The journey transforms you from a macroscopic object to a quantum superposition of possibilities that current physics cannot fully describe. From outside, you appear frozen at the event horizon forever, your information smeared across the boundary, eventually released in some form through Hawking radiation as the black hole evaporates over timescales longer than the current age of the universe. From your perspective, the journey takes finite time, ending in destruction by tidal forces that increase without bound until reaching densities where space-time itself becomes quantum and uncertain. Both perspectives are valid within their reference frames. There's no absolute answer to when and how you meet your end. The timeline depends on whose clock measures it, and general relativity teaches us that different observers can experience reality in genuinely different ways while both being correct. This is the complete timeline of falling into a black hole, a journey from normalcy to impossibility, from the familiar physics of planetary orbits to the strange regime where time and space exchange roles, where all futures lead to a singularity, where information faces destruction or transformation in ways that challenge our deepest physical theories. It's a one-way trip through a boundary of knowledge, ending at a place where physics as we understand it breaks down completely. You begin intact, curious, approaching a cosmic mystery. You end as disconnected particles, or perhaps as information encoded on a horizon, your fate depending on quantum processes we don't yet understand, your timeline split between perspectives that never reconcile. This is what awaits anyone who crosses the event horizon, the ultimate transformation from order to entropy, from structure to singularity, from existence to whatever lies beyond the boundary of space-time itself. The black hole timeline is a journey that physics can describe but not complete, that mathematics can formalize but not finalize, that represents both the triumph of general relativity in describing extreme gravity and its failure at the very extremes it predicts. It's a timeline that ends at a question mark, at a boundary where our current understanding fails and something deeper must take over. And perhaps that's the most honest answer physics can give. We can trace your path to the edge of knowledge, but beyond that edge, in the heart of the singularity, only questions remain.